Hello and welcome. The lecture today is on trigonometry, and I have to say this is one of my favorite questions of all time kind of thing. If I had to pick sort of like, I don't know, top 10, top 20, this is one of them. I think it's a really beautiful question. It's been with me not a very long time, probably around 2014. I think I came across it, and I loved it ever since. Let's actually read what he actually says. Sorry, I printed it a little bit small, but I will write the important things down. He says the positive solution of the quadratic equation x squared minus x minus 1 is equal to 0 is denoted by phi and is commonly known as the golden section or the golden number. Those who are kind of like maths connoisseurs, they're aware of this fact. It can be shown, and you may assume in this question, that the cos of pi over 5 is in fact half of this number phi. Okay? And then it says use trigonometric identities to show that the tan of pi over 5 times the tan of 2 pi over 5 times the tan of 3 pi over 5 times the tan of 4 pi over 5 is equal to 5. And it does say you may not use complex numbers in this question, because this type of questions and results like that can be done using complex numbers by kind of like using certain techniques which most of us are familiar with. So let's record the bits of information. So x squared minus x minus 1 is equal to 0 has solution phi, the golden number. So the positive solution of this particular quadratic is denoted by phi. And further to that, we're being told as a matter of a given that the cos of pi over 5 is in fact half phi. So these are information that is being given to us. Okay, and we need to show a chain of loads and loads of tans is in fact equal to 5. So tan of pi over 5, tan of 2 pi over 5, oops, keep writing plus, tan of 3 pi over 5, tan of 4 pi over 5, that should turn out to be 5. We could go with tangents. The reason I probably will not is because a lot of people don't have the concept of the tan, what it actually represents in on a diagram. It's actually gradient. For example, I don't know how many people would have known here. For example, if you look at, let's say, a quadrant diagram, pi over 5 is 180 divided by 5 is every 36 degrees. So it's like that, 36, 72, 108, 144, and so on. So that is the tangent of pi over 5 here. And the tangent of 4 pi over 5 has exactly the same gradient but negative. So I can actually replace the tan of 4 pi over 5 with the negative tangent of pi over 5. But probably it would be better off to work with sines and cosines that we are more familiar with. In the same way that 2 pi over 5, which is here, can be replaced with the 3 pi over 5 or vice versa. So let's work with sines and cosines and take it from there. So at the moment, I don't know if that's equal to 5. I'll prove it that it is. So far, sine pi over 5, somewhere I write is sines and coses basically. Wasting time, perhaps. Sine 2 pi over 5. And let's think while I'm copying that as to what our next step will be. In fact, I gave a clue with the tangents as to what our next step should be. It's just that we have better working knowledge with sines and causes. Okay, over the cos of 4 pi over 5. Okay, what do we know now about sines? The sine of theta is of course the same as the sine of 180 minus theta, or if we're in radians, as we are in there, pi minus theta. So the sine of 4 pi over 5, I can actually write it, and I do apologize because I'm writing a lot of unnecessary stuff over and over again. This is of course the same as the sine of pi over 5. Okay, pi take away pi over 5 will give us 4 pi over 5. The same way, the sine of 2 pi over 5 and the sine of 3 pi over 5, it's exactly the same. I'll keep it in its simplest or with the smallest argument. So that's already there. And I'm going to replace with this equivalent 2 pi over 5. So in fact, that we're going to have a sine squared of that and sine squared of that eventually. What happens with the cos is the next thing. The cos of theta is equal to minus the cos of 180 minus theta. A lot of these things can be verified, of course, using your compound angle and so forth. So for example, if you think about having the cos of 30 and the cos of 180 take away 30, which is 150, the negative of one another's. Okay, or if you had the cos of 40, that's the same as minus the cos of 140, and so on. So if you look at what we got there, the cos of 4 pi over 5, which is here, I can actually write here as minus the cos of pi over 5. The same way, I'm going to leave the cos of 2 pi over 5, and I'm going to replace that, because of course the minus, I hope it doesn't confuse you, I can put it with a small number, it doesn't really matter. Cos of 2 pi over 5. So I replace it to have nicer quantities. Okay, so far so good. I could have done that straight away and a lot quicker with tans, but I just explained at the very beginning. A lot of people might not have familiarity with the tangent, so I've done it with sines and cos. It's also important to actually see these kind of things. So what we're going to end up with here is sine squared of pi over 5, that times that, and of course sine squared of 2 pi over 5. And the minus times the minus will go plus, and we're going to have exactly the same thing. Cos pi over 5, cos pi over 5, and of course, cos squared of 2 pi over 5. Okay, where do we go with this? Where we're going with this is, first of all, we're going to cos of pi over 5, because these things are all half pi's. And at the moment, this thing only appears in this quantity here. It doesn't appear there. And then worse still, we have sines rather than causes. So the first thing to write down is, I'm going to write the identities here that I'm going to use. So we're all happy. Sine 2 theta is 2 sine theta cos theta. We all know that. And I'm looking at this quantity here, forget about the square, sine of 2 lots of pi over 5. So the sine of 2 lots of pi over 5 will be 2 sine pi over 5 cos pi over 5. And the same thing, if you look at cos of 2 theta, and I don't want to go cos this or sines, I want to go cos this, so that's 2 cos squared theta minus 1. Then if I use it to break down the 2 lots of pi over 5, that'll be 2 lots of cos squared of pi over 5 minus 1. Okay, let's put these things in and let's see what happens. So I have to be very careful there because there's a few squares and we must not make a mistake. So first of all, sine squared of pi over 5, just merely recopied. This is of course this quantity which is here, but let's not forget this is squared. So I need to square this expression. So it's going to be times 4 sine squared of pi over 5 cos squared of pi over 5. I hope you can see where this came from. I squared that and I placed it in there. This is already a cos squared of pi over 5, which is rather nice. But this is 2 lots, so that's this bit here. So I'm going to put a bracket, so it's going to be 2 cos squared of pi over 5 minus 1. Okay, let's rub off these things here. And let's hope things begin to shape up. I'm hoping for some cancellations because it's getting quite involved by the looks of things. So first of all, this cancellation is quite obvious. That has gone. And already made a mistake. If you look at this quantity here that I shoved inside this bracket, that is the bit without the square, so that should be squared there. So it's already a mistake there that I could have made without spotting it, and then I'll be pulling my hair. So these two things have actually gone. Okay, and what else have I got left in there now? I've got a 4, and now I have a sine. Shall I write it straight away, or shall I just... No, I'm going to write this. Each of these sine squareds is using an identity, of course, the most famous identity, 1 minus cos squared of pi over 5. So that's this bit here. But of course, I go 1, 2, so it's squared. The 4 is from this bit here. And this quantity here, let's, for the time being, leave it as it is before I do any more tidy ups. Because you should be able to see now, in here, I've got cos squared pi over 5 and cos squared of pi over 5, which can be replaced by half phi. So, time to clear the board, go right to the top, lose all this kind of stuff, and let's see what happens. I hope you're still with me and you're following what I'm doing. So this is 4, 1 minus. Now, the cos of pi over 5 is half phi. So when I square it, it's going to go quarter phi squared. So this is, in fact, 1 minus a quarter phi squared. And of course, all of that is squared. That's from the square there. And on the denominator, we got 2. The cos of pi over 5 is again a quarter phi squared. So that's 2 times that minus a 1 and then all squared. Tidy up time. Okay, so what I'm going to do there, probably erase the line. I'm not squaring that, and you will see why just yet. And that's half phi squared minus 1 all squared. And now time to factorize a quarter out of this bracket, but the quarter is squared, so it's 1/16 when it comes out. 4/16 gives me a quarter on the top, and this now becomes 4 minus phi squared or squared. So that's exactly the same. And from here, I can factorize again this a half out, but because the squared is going to give me again a quarter. And what I'm going to be left with is phi squared. I pulled out half, so it's going to be minus 2 all squared. And again, the quarters will cancel. Gone. Okay, where do we go now with this? Is the next question. If the quadratic equation x squared minus x minus 1 is equal to 0 has solution phi, then that clearly, this means x squared is equal to x squared, rearranging that, is equal to x plus 1, which means squaring your phi is exactly the same as taking your phi and adding 1. So rather than squaring all this bracket, what I'm going to do inside that bracket that I'm seeing in there, I'm going to say 4 minus 5 minus 1. I replace the 5 squared with 5 plus 1, all squared. And I'm going to do exactly the same thing on the denominator. 5 plus 1, that's the 5 squared, minus 2, all squared. So I lost at least the squares inside this bracket, so I have less squaring to do. Okay, tidy. 3 minus 5, all squared, over 5 minus 1, all squared. I think it's good so far. Let's expand it. 5 squared, squaring the brackets, minus 6, 5 plus 9, and on the denominator 5 squared minus 2, 5 plus 1. And again, I'm going to do what I just done in there. 5 squared is 5 plus 1. So 5 plus 1, that's this 5 squared, minus 6, 5, plus 9, and again 5 plus 1, minus 2, 5, plus 1, tidy, 10, minus 5, 5, on the denominator we have 2, minus 5, and I think we're done. I have enough room to do it here. Factorize on the top a 5, that will leave us at 2 minus 5, 2 minus 5, boom, boom, 5, as the question requires. I hope I presented it well. I've got this feeling maybe I rushed in my excitement. I've told you this is one of my favorite questions that involves the golden section and manipulations of trigonometry, and I hope you followed what I've done in there step by step. I will advise you, if you didn't, to actually go through the video bit by bit, pause it and see if you can find your way around, because I think this is a really beautiful question. Okay, enough of this. I will be signing out. I'll see you real soon for more maths. Bye for now.